In this class, what we're going to be doing is we're going to be taking a look at a form of power cycle called the gas power cycle. And so what we've done thus far in the course is we have performed a review of thermodynamics. We've looked at the first law, we looked at the second law, and we also looked at exergy. So with that, what we have are all of the tools that we can now start to apply to mechanical engineering systems. And so this lecture is the first part of, really, I guess you could say, the second half of the course, and looking at applications of all of the theory that we have thus far developed and all of the tools that we have, property data, the equations. So we're now going to start with gas power cycles, which are probably one of the most common known thermodynamic systems that each of us deals with daily, because these are the systems that are used to provide power for cars or automobiles, planes, buses, trains, unless it's an electric train. However, if it's using any kind of fuel, it would be using a gas power cycle. So what we'll be doing is we'll be taking a look at gas power cycles in today's lecture. And so the key thing here is that the gas power cycles are producing power from a heat source, so that's one thing. The other thing to note is that the working fluid in these systems remains a gas. We will be looking at other power cycles later in the class called the vapor power cycle. The most famous of that is the Rankine. Rankine cycle is used in steam power plants and steam engines of old. And there what is happening is your working fluid goes through a phase change. So you would go from a liquid to a vapor state. However, here what we're dealing with is a system whereby the working fluid in our cycle remains in the gas phase. Now, I guess technically you could argue that if you have a liquid gas, like gasoline or diesel fuel, you're injecting that. But what we do is we atomize that when we inject it into the airstream. And so we can consider the working fluid to be a gas for these cycles. So examples of these gas power cycles would include the following. We have spark ignition engines. And these are engines where you have what we call a spark plug. And what the spark plug is, it's a gap between two metals, and you put a high voltage across it and you'll get a spark forming. But that is what initiates the combustion within our cylinder. And so consequently we call those spark ignition engines, which tend to be quite popular. They're used in a lot of cars. We have diesel engines, which by comparison to spark ignition, these are actually compression ignition engines. And here our pressure ratio is going to be higher, and what happens is you compress the charge, so the gas fuel, the fuel air mixture, to a high enough pressure, and there's also a glow plug in these engines, but that will initiate the combustion process. So it's compression ignition engines. And in a later lecture, I'll let you hear these, and so you can hear the difference between a spark ignition engine and a diesel or compression ignition engine. Another form, which is really a very, very different design from both spark ignition and compression ignition, are gas turbines. But these also fall under the definition of gas power cycles. Gas turbines are used in industrial applications for power generation, but the one that you're probably most familiar with would be the one that's hanging underneath, let's say, the wing of a 777 or of an A380. Those are gas turbine engines, and they are what provide the propulsion for the aircraft when it's flying, but they're also used for other applications, like I mentioned. Gas transmission, pipelines use them for power production. Typically when you're above about the 30 megawatt range, that's when you get into the gas turbine engines. But they're also used for stationary power production, peaking power for electrical utilities, things like that. But these engines, all three of these, or cycles I should say, the thing that is in common here is the combustion process is taking place inside of the engine. And so these are internal combustion. Engines or cycles. And that is contrasted by two other cycles that we will study, one being the Stirling cycle, or Stirling engine, and the other is the Ericsson cycle, or Ericsson engine, and these are external combustion engines. And so here what happens is you're burning or combusting, you're oxidizing your fuel mixture outside of the engine, and that generates the heat, which then goes through heat transfer and heats up the working fluid inside of the engine. But that's a different design of engine versus the spark ignition, compression ignition, or the gas turbine, which is actually the Brayton cycle. With those, you have combustion inside of the engine. So when we're doing our calculations, we're going to have to make some assumptions here because these cycles are very complex, and in order to do our basic analysis, we need to simplify things. So what we are going to be doing is doing what we call ideal cycle analysis. And I will write down what the different components of ideal cycle analysis are. First, we assume that there is no friction, and by friction I mean both mechanical, so mechanical friction within the moving parts of the engine, or fluid friction, so that would be pressure drop as the working fluid moves throughout our engine. So we're assuming there's no friction. We're assuming that things are operating in a quasi-equilibrium manner. And that's typically for our expansion and compression processes. Expansion is where you get the power. Compression, you have to put the work in order to compress the air or the air-fuel mixture. Another thing that we will assume as part of ideal cycle analysis is that heat transfer is negligible. When not intended. Now we will have heat transfer, and I'll talk about that in a moment. That's how we actually heat the working fluid. But where would it be negligible when not intended? That might be the pipes that are connecting one component of the engine cycle with another. So I'll just write here pipes connecting components. And another assumption that we will make as part of ideal cycle analysis is that heat transfer is going to be through a finite temperature differential. And what this means is that the cycles that we're analyzing are not externally reversible. In order to have it externally reversible, we would have to have heat transfer through an infinitesimal delta T, which we said is really not practical for real engines or any kind of cycle that we study. Okay, so those are the things of the ideal cycle analysis. The other set of assumptions that we will make when we look at gas power cycles are called the error standard assumptions. And what these state are the following. The first is that the working fluid in our engine is assumed to be air. And we'll assume it to be an ideal gas under the conditions that we're looking at. And that it circulates in a closed loop. Now we know this is not true, because for any engine, the air comes in, fuel is added, it combusts, and then it exhausts out. But we're going to assume that it operates in a closed loop. So that's part of the error standard assumption, and it enables us to be able to do our analysis, otherwise it'd be too complex. Another assumption that we will make is that all cycle processes are internally reversible. Now, we do have combustion, but we're assuming the working fluid is air, and consequently we do not take into account with this error standard assumption that we have a fuel-air mixture. But what we'll assume is that combustion processes are replaced by we're going to assume that they're replaced by a heat addition process. And we're going to assume that this is coming from an external source. And the other thing that we will assume is that the exhaust cycle, or the exhaust component of our cycle, is replaced by heat rejection. And that enables the working fluid then to cool down. In reality, with these engines, what we do is we purge it. We dump it into the atmosphere, and we draw in a new fresh charge of air, and then we mix it with fuel. But what we'll assume is that there's a heat transfer process that takes place, and that enables us then to do a cycle analysis for whatever cycle we're looking at, be it the internal combustion engine with spark ignition, compression ignition, or Brayton, or the Stirling. And the last assumption that we will make, and sometimes we'll make this, sometimes we won't, and that is the cold air standard assumption. Sometimes you'll be working a problem where it says using the cold air standard assumption, so just pay attention to that. And what does that mean? What the cold air standard assumption means is we assume something about the specific heats, and that is that Cp and Cv of air are taken to be at 25 degrees Celsius and constant. If you cannot invoke this cold air standard assumption, what you will need to do is you will need to account for variable specific heats. And typically the temperature differential in any of these engines is going to be more than 200 degrees Celsius. Consequently, you need to use the tables in the back of the book, usually when you're solving either any of the engines, so the internal combustion or even the external combustion problems. So those are some of the assumptions that we'll be making as we go through solving gas power cycle problems.